Enthalpy of formation is an important idea and is fundamental to understanding Hess's law. So the first thing we need to consider is what are they? And then how do we use them? What are they good for? So I want to start with the word enthalpy. Enthalpy is the hidden heat, the hidden energy. What do I mean by hidden? Well, some energy we can see. Total energy equals potential energy plus kinetic energy. Average kinetic energy can be measured. It is related to the temperature, but it has to be in an absolute scale, temperature in Kelvin. So I can see the average kinetic energy by measuring the temperature with a thermometer. But potential energy changes have to be figured out indirectly. Potential energy is the hidden energy I'm talking about here. It is the energy by virtue of position or composition. And in chemistry, we're considering composition. And then when composition changes, there are changes in potential energy. When chemical reactions occur, there are changes in potential energy. Okay, so here we have a table, and this is similar to a table that you have in your book, Appendix 2. And I'm mostly focusing on this area. And we're considering the changes in enthalpy of formation in the standard state, these numbers. Delta G has to do with, is this spontaneous? Will this be spontaneous? S has to do with, has the entropy increased? These are important concepts, but these are concepts that we will deal with in Chem 1B. In Chem 3A, 3B, we only focus on the first column. So what is the change in enthalpy, potential energy at constant pressure, of formation for a compound from its elements in standard state? What is standard state? That's just where we live, at 1 atmosphere of pressure and about 298 Kelvin, which is room temperature. And if we had a concentration of a solution, it would be a 1 molar solution. If it wasn't pure, if it was mixed with water. Okay, so I want to focus on this formation idea. We're forming 1 mole of a compound or an ion or something that isn't the element from its elements at standard state. And standard state is just room temperature, pressure, and if it's a solution, concentration of 1 molar. So let me start with ammonia. If I was going to write the equation that represents this number, I would say I'm forming 1 mole of ammonia. That's a G, so I'm making ammonia gas. Forming 1 mole of the compound from its elements at standard state. The elements in ammonia are nitrogen and hydrogen. In their standard state, those are diatomic molecules. Those elements are diatomic, and they're both gases. In order to have 1 nitrogen, I need to have half a mole, or 1 mole of ammonia. I need 1 mole of nitrogen, which is half a mole of the molecule. And for 1 mole of ammonia, I need 3 moles of hydrogen, but hydrogen comes in pairs, so this has to be 3 halves. The formation equation for ammonia as a gas is written here. A formation equation is the formation of a compound or an ion from its elements in their standard state. The formation of 1 mole. Is that how we would normally write this? Probably not. If we were making ammonia, we would say, well, we need nitrogen gas and hydrogen gas. And then to balance it, we would recognize that ammonia has hydrogens that come in group of 3s, but hydrogen, the element, comes in group of 2s. So let's shoot for 6. Let's have 3 moles of hydrogen gas to form 2 moles of ammonia. Now I have 2 nitrogens and 2 nitrogens. There is my balanced chemical equation. So the equation we would write for stoichiometry would have whole number coefficients. But for a formation equation, we must have 1 mole of the product from its elements and standard states. So it's a little bit different. What does a positive enthalpy mean? Well, if we were making nitrogen monoxide, the enthalpy change would be positive. If we were forming 1 mole of this gas, we would need a half mole of the element nitrogen in its standard state and a half mole of oxygen in its standard state. To form 1 mole of the gas. There is a thing called a reaction progress diagram. That will be important in science. And we have the before here, moving to the after there, so left to right, just like we read. And on the y-axis, we're looking at an increase in hidden energy or potential energy. If we have a positive value, what that means is the reactants started at lower potential energy and work was done, energy was put in to create products that are at higher potential energy. So when we have a positive enthalpy value, that means to form this product, work was done. How much work? Well, the difference between final and initial. And that difference in potential energy is the difference in hidden energy, potential energy, and in this case it's positive. Final minus initial gives us a positive number of 91.3 kilojoules per mole. So a positive enthalpy means energy, hidden energy was added to get the reactants to the products. The products are in a higher potential energy state. Now, what are these numbers? What is the actual starting place and ending place? We don't know. We don't know because potential energy is too hard to quantify when it's an electrostatic field that acts on charges in these complex systems that don't sit still. We do know, though, the change was positive. Work was done. We ended a higher potential energy state. What does a negative enthalpy mean? Opposite idea. So here we're forming water as a liquid, and there's a negative enthalpy. That means we started with hydrogen and oxygen are the reactants. And we're going to look at the reaction progress and the changes in potential energy. When they broke their bonds and made new bonds to form water as a liquid, one mole of hydrogen gas, half a mole of oxygen makes 1 mole of hydrogen as a liquid. This is an enthalpy of formation equation. And these are numbers that go with that process. And if it's negative, that means our final was lower than our starting place. So here we have initial enthalpy, final enthalpy. A difference in enthalpy is final minus initial. And if final is small, if final is lower than initial, we get a negative number. What are these actual numbers? I don't know, but I do know that the difference is 285.8 kilojoules for every mole. So a negative enthalpy means that we went for reactants. When we went from reactants to products, potential energy was lowered. If total energy equals potential energy plus kinetic energy, if potential energy goes down and total energy stays the same, kinetic energy went up. What does that mean? It means the temperature went up. In an exothermic process, heat is released. How do we use these? Well, we can take these enthalpies of formation and we can come up with an enthalpy for a reaction. So here I have hydrazine as a gas, and I can find the value for that on my table. So we have 3 moles of hydrazine at the formation of this was 95.4 kilojoules per mole. And they react to form. Bonds are broken, new bonds are formed, and we make ammonia. Ammonia is a gas. We have 4 moles, and then the value for the formation of the gas is 45.9 kilojoules per mole. We also have nitrogen as a gas, 1 mole of that. But elements formed from elements in their standard state, there's no change. They started as elements. We're looking at them as elements, 0 kilojoules per mole. So to figure out what the overall enthalpy of reaction is here, I'm going to do a calculation called Hess's Law. Hess's Law, and it looks like this. I take the sum of the moles times the enthalpy of formation for the products minus the sum of the moles times the enthalpy of formation for the reactants. So, and if I add all of those together, I'm going to get the enthalpy change for this reaction. So the sum of the moles of the products is 4 moles, and the enthalpy of formation for ammonia is negative 45.9 kilojoules per mole. And 1 mole of nitrogen at 0 kilojoules per mole. So that equals 0. Minus, and now I'm going to look at reactants. 3 moles. Each mole is 95.4 kilojoules. When I add all this together, I will have the enthalpy of change for this reaction, and that's my goal. Hess's Law is to solve for the change in enthalpy for a reaction, and we can do that starting with enthalpies of formation. Okay, so 4 moles times negative 45.9 kilojoules per mole is negative 183.6 kilojoules. Minus 3 times 95.4 kilojoules per mole is negative 286.2 kilojoules. Combine those. Negative 469.8 kilojoules is the energy released when this reaction happens. We can use this number for stoichiometry. If we started with a certain number of grams of hydrazine, we could convert that to moles of hydrazine. We could recognize that every time 3 moles of hydrazine are consumed, this many kilojoules of energy are produced in this exothermic reaction. And we could come up with a number. So this would be stoichiometry with enthalpies. Let's do that problem. Let's say that we had 10 grams of hydrazine. Let's do that problem. Let's say that we had 10.0 grams of hydrazine. We look up the molar mass, and we see that it's 32.06 grams per mole for hydrazine. And the question might be, if 10 grams are combusted, how many kilojoules of energy are produced? So it begins like any other stoichiometry problem. 10 grams of this reactant. I use the molar mass to convert to how many moles of that reactant we have. And now I'm going to use this coefficient 3 every time 3 moles of hydrazine are combusted. And this energy that we found, negative 469.8 kilojoules are produced every time 3 moles are consumed, and find out how much energy is produced. And I came up with, let's see, 3 sig figs, negative 48.8 kilojoules of energy are produced.